mass extinctions recurring every 26 to 30 million years, as far as the rock remembers. Whilst the Sun has been making the same journey for 4.6 billion years. Not just the orbit most people know about. The Sun traces a long ellipse around the galactic center, but there's another motion buried inside that one, a slower rhythm. The Sun dives under and out of the galactic plane gently. One full period, one full breath every 60 million years. That is, to be submerged in the galactic plane every 26 to 30 million years. And every time it passes back through the plane, every time it dives, it moves through the densest parts of the disk. Molecular clouds, stellar nurseries, gravitational disturbances that reach all the way to the outer edge of the solar system, where billions of icy objects have been sitting in the dark, completely undisturbed since the beginning. And some of them get shaken loose. Some of them fall inward. In 1984, Rope and Sipkowski published an analysis of marine fossil genera and argued the extinctions showed a periodicity of roughly 26 to 30 million years. The same year, Rampino and Stothers published a paper claiming that timing was strongly correlated with something else entirely: the Sun's vertical oscillation through the galactic plane. This idea is later known as the Shiva Hypothesis, named after Shiva from Hindu mythology, a god of cosmic destruction, renewal, and rebirth. Although recent research debates that it's contested and correlation isn't perfect. But what if it was? If humanity ever finds out that the Shiva hypothesis is true, that is, if moving through the galactic plane is caused by gravitational disturbances of millions of stars within a few hundred light years, all the molecular clouds and more, hurtling millions of icy asteroids and comets that will eventually rain down on Earth, causing a mass extinction periodically. What can we do about it? Could we move the Sun and the entire solar system? To make our solar system stay above the galactic plane at all times, preventing mass extinctions. To hold the Sun above the galactic plane, the force needed is in the order of 10 to the 20 newtons. That is, to resist the gravitational pull of the mass of the galactic plane. That's the price of refusing gravity. However, we also have to be accelerating the Sun slow enough such that the planets can keep up with it and not cause orbital destabilizations. To stay bound to the Sun and move along with it, instead of being left behind. One intuitive way in pop culture science is to push the Sun by shining its own light on itself. This single equation tells us that light carries a momentum, where the force F equals to the luminosity L divided by the speed of light, c. Why does this matter? Well, the Sun has a luminosity of approximately 3.828 times 10 to the 26 watts. Divide that by the speed of light, gives around 1.3 times 10 to the 18 newtons of force, leaving the surface every single second, in every direction outwards simultaneously, symmetrically. Which means the radiation forces cancel out each other and the Sun stays in the same place, ignoring the planets tugging on the Sun. This idea is commonly known as the Shkadov thruster, a giant mirror that focuses the beams of the Sun onto itself. However, this method is futile in moving the Sun fast enough within the 30 million year constraint. The Sun is incredibly massive. If we somehow directed 100% of this enormous amount of force to the Sun for a million years straight, it would accelerate the entire solar system by 10 meters per second. Obviously, extremely slow. Even a star converting mass into energy at nuclear efficiency produces 2 orders of magnitude too small of force. The answer is to stop pushing at all and start throwing mass. And the Sun itself contains approximately 99.86% of the total mass of the entire solar system. So, we could use the Sun itself to push itself like a rocket. A rocket that already has fuel inside, then ignites itself into a focused direction. A rocket does not care whether its fuel is chemical, nuclear, or stellar. It only cares about momentum. Now the problem changes. No longer photons, mass, plasma, hydrogen, helium. The sun's own skin, peeled off and flung backward at incredible speeds. The force governing this is no longer L divided by C. It is F equals dm over dt times v, the change in mass over time multiplied by the exhaust's velocity. Momentum depends on these two variables: how much mass is expelled per second, and how fast the mass is moving. Both are, in principle, controllable. The sun already provides one of these for free. The second, velocity, can be increased by extracting energy from the system and using it to accelerate the plasma through magnetic field structures acting as nozzles. This is a solar reaction mass rocket, to turn the sun into a rocket engine. But we need to know if obtaining this amount of force is possible to combat the Milky Way. Well, the force needed to combat our galaxy's gravitational pull is exactly the force it pulls on the sun, which is about 10 to the 20 newtons. Plugging that to the equation gives dm over dt equals 10 to the 20 newtons divided by v. This is the core trade. To reach this quota of newtons, our astro engineers and physicists have to find the optimal balance between two variables: how much mass of the sun we would have to eject versus how fast we eject it to give the same momentum, the same force. Run the exhaust at low velocity and you need a high mass flow rate, dm over dt. More plasma leaving per second. But this causes its gravity to weaken over time. Planetary orbits expand and eventually destabilize. Run the exhaust at high velocity and the mass flow rate drops. The sun mostly retains its mass and the gravity holds. However, more energy per mass of the sun must be extracted from itself and redirected into accelerating that mass in the first place, because that velocity just doesn't come out of nowhere. You need some energy to actually accelerate the sun's mass. In both scenarios, the same amount of energy is needed for the same outcome. Hence why thinking in terms of energy is so useful, because it is independent of the path taken to get to the outcome. If managed correctly, the drain is gradual enough such that the sun survives across billions of years. The galactic plane crossing that has been arriving every 26 to 30 million years stops. In the reference frame moving with the sun, everything in the solar system experiences a slight, constant tilt in the effective gravitational field. If that tilt changes slowly enough, the system adapts. Orbits deform, but they do not break. So the requirement is not just force, it is control. Continuous, directional, and slow enough such that the solar system remains internally consistent across millions of years of gradual change. However, the big question is, how long can we maintain this engine for until the sun loses enough mass to cause a solar system-wide orbital destabilization? If the sun loses 1% of its mass, everything would relatively be unchanged. At least not enough to kill all of life. Earth's orbit would just be around 15 days longer, 370 instead of 365 days. With this, depleting that much mass would take 600 million years from the solar reaction mass rocket alone, letting the current life on Earth avoid 20 mass extinctions. Nothing about this engineering is free. Lifting plasma from the sun and accelerating it through a magnetic nozzle requires energy, and that energy has to come from somewhere within the system itself. The sun is both the thing being moved and the power source for moving it. It is a constraint. The rate of mass ejection is bounded by how much energy can be extracted and converted into directed motion, without disrupting the processes that keep the sun stable. Eject too little and the force is negligible. Eject too much and the sun's internal balance shifts in a way that affects its luminosity, its output, and stability. Every intervention in a system this large has consequences that propagate across timescales longer than human institutions have ever maintained coherent purpose. The engineering is not the hard part, continuity is the hard part. The project requires a civilization to maintain a single direction intention across millions of years, maintaining structures, correcting drift, monitoring the star's response to interventions whose effects will not be measurable in any single human lifetime. Every generation inherits a machine they did not build, serving a purpose they were told rather than experienced, aimed at a threat that will not arrive in their lifetime, or their children's, or their children's children's. This is a different kind of engineering problem from anything humans have ever attempted. Not harder in a physical sense, but harder in a sense that requires something from the builders that no structure or equation can guarantee. The physics is the easy part. The physics does not forget. The physics does not change priorities, does not lose funding, does not decide that a threat arriving in 26 million years is someone else's problem. The sun is still bobbing. The crossing is still coming. We have the orbital mechanics. We have the plasma physics. We have the magnetic field dynamics. The equation F equals dmdt times v is not speculative. It is the same rocket equation that moved every single spacecraft humanity has ever launched, scaled to a different problem. The Shiva Hypothesis is contested, but the oscillation is real. The mechanism for perturbation is real, and the extinction periodicity in the fossil record is a measurement, not an interpretation. What does not yet exist is the decision. Not the technology, not the physics, not even the institutional architecture. Humanity has maintained continuous scientific programs across centuries before, and the principles for extending that are not mysterious. What does not exist is the moment when a civilization looks at the schedule written in the rocks beneath its feet, looks at the equations that describe how to rewrite that schedule, and decides the distance between those two things is worth crossing. We are the first civilization that has existed on this planet, with the physics to understand what that decision involves before making it. Every previous generation that faced this, if any did, faced it without the orbital mechanics to read the threat clearly, without the plasma physics to understand the response, without the geological record detailed enough to confirm the rhythm. We have all three. We have had them for less than a century. That is an unusual place to be. Not powerful enough to build what the problem requires, not ignorant enough to look away from it. Exactly positioned at the moment of understanding, after the physics arrived, before the answer was given. The rock still has the rhythm. The sun is still on its way back through the galactic plane, and somewhere in that gap between the pattern is an ancient stone and an equation on a page. There is a question that belongs specifically to this moment in history, whether understanding a problem clearly enough to solve it is the same thing as deciding to.